If there is, we will need to stop the recording. I've just started the recording now. So without further ado, really, I want to introduce the CEO of OpenRemote, the developer of the interoperable energy management system, who will give a run through and a visualization of what the core features of this system is. This system has cost a considerable amount of development money, and it does have a future focus in mind to renewable energy sources, how you link those and drive down renewable energy costs. So for any cities out there that either have a strategy around renewable energy sources or a strategy around increasing electric vehicle use, etc., this system will be able to optimize the facilities that you may be looking to introduce in the very near future. So I'll hand this over to Pierre, and Pierre will run through a presentation. We will finish up with the Q&A. As I said, I really don't want to be asking all the questions. I want the questions to come from the participants. So please hit those in the chat. And without further ado, Pierre, it's over to yourself. Thank you.
Thank you, Chris, for the introduction. As mentioned by Chris, I'm Pierre Kil. I'm heading OpenRemote, and OpenRemote is the developer of a completely open source platform solution. And in the context of clean mobile energy, we've added features and functionality to make it suitable for a complete interoperable energy management system. And as mentioned, in this presentation, I want to quickly give you an overview, but also show you the live pilots at their current state in the different pilot cities. You should be able to see a brief presentation here now. So this is a picture of Arnhem, by the way, and in the upper corner you see the harbor and the field where solar panels and winds are being allocated. And shore power is one of the items which we're controlling within the iEMS. Before showing any examples, first obvious question is, what is an EMS or an interoperable EMS? The elements of an energy management system. So with this picture, I want to give you a quick overview. In the middle, you see a picture, and actually the objective of an energy management system is to connect renewable energy sources. We're talking electricity in this case, electricity consumers, optional battery storage devices, and the network and the grid and the energy supplier. And the objective of this all is to optimize the system in such a way that you're maximizing the local renewable energy usage and limit the capacity on the overall meter over which you are receiving and feeding back your electricity. Going through it briefly before showing again is starting at the upper left. So in terms of optimization, what the EMS is capable of doing is treat, first of all, multiple islands being combinations of the systems indicated in the middle behind a single meter, and then target for either financial or carbon exhaust optimization. And it does so by controlling batteries, controlling charging sessions of connected vehicles, or sharing profiles with consuming devices to limit their overall consumption. The second element, renewable production. So the system connects live to renewable production like solar or wind, and in addition forecasts with the forecasting service the power production of these services as it's being required to do a proper optimization. The battery, bottom left, is one of the controllable devices. If a battery is connected, it will charge and discharge at the proper times, and it will also take into account the optimum price point. So in case of agile tariffs from your electricity supplier, that would be relevant to maximize the financial savings. On the upper right, control of V2G charge sessions, V2G, so of course regular EV charging, but also V2G, so vehicle to grid charging. Here also it's relevant to have live connection, and we have live connection to the meters of the chargers and vehicles. And based on a schedule, if we're talking about fleets within a city, owned electricity fleets, electric vehicle fleets by the city, then fleet managers can set an energy schedule, and that's relevant as it would define the prioritization and scheduling of the charge sessions. In the end, a vehicle has to drive, so you should prevent that it runs empty while it's being needed. Electricity supply, import and export tariffs are connected, same for carbon. And we can link here to dynamic pricing if the contract offers you dynamic pricing. And the last item, the electricity grid. Of course, there's a limit to the import capacity, and you can set that to prevent that the overall demand or feedback into the grid exceeds these limits. Having said this in brief, I want to show you a few examples. So if I'm correct, and please correct me if not, then you should be looking at the Nottingham city pilot. And what you're first of all seeing is a map view. This is Eastcroft Depot in Nottingham. It's one of the sites of the Nottingham City Council, at which there is, as you can tell from the picture, there's several solar installations on the different roofs of the buildings. And there is a range of vehicles. I think there are about 40 electric vehicles from the city of Nottingham currently connected, of which you see their live locations, but more importantly, we're live connected to those. And having that connection to these vehicles and the chargers, and of course knowing when these are connected to the chargers, plus the connection of a battery, which you're seeing here in the middle, allows us to optimize the V2G charging in this case in combination with a vehicle battery. Now, how that works, let me quickly move from the map view to the asset view, which is the second tab at the top. And what you're seeing here, and you'll see it in the other locations as well, basically you see on the left here a structure of what's called an optimization group. So the optimization which I just described will be applied to each group and what we call assets, so object under that group. And in the Nottingham case, you see that storage device. And as you can see from the history graph here, you see a charging and energy level going up and down twice a day. The reason being is there's an agile tariff in Nottingham. So the optimization decides that at 2 cycles on a 24-hour basis to make maximum use of this battery by charging and discharging this battery. Going back to the structure on the left, you see the chargers. You see the vehicles being live connected, and on the buildings, on the production side, you see the 3 buildings which all have solar panels on these buildings. Quickly showing the additional features in here. There's an optimization routine which itself you would only see the results of it. So you see that currently there's a saving of £280 purely due by using of in this case the battery, as the vehicles are not yet actively being charged by the optimization. So it's currently the battery usage which causes a financial saving by shifting energy supply and feedback, and the differences in tariffs. So that's shown on this optimization. What I can show is the third tab here is the rules, and rules is a way for users of the system to add their own logic to the system, and there are 3 ways of doing it. In this list there you see when then rules, flow rules, and groovy rules. The example which I have here, and I'll show the other ones later, is groovy. So you see 3 types of groovy, and mind you, this is a more usage by technical, more advanced users. This gives a scripting language for application managers to add their own logic to the system. So it can be a kind of optimization or whatever logic you would want to apply in your system. I will show the simpler, more simple rules when then and flow in a minute in another example. But the last part I wanted to show here is the insight page. So this insight page is a basic overview of the performance of the system, and it can be set yourself. So I've just configured it to save time here, but you can select your own attributes in the system and decide how you want to show them and where you want to show them. I've prepared them to just show in this graph how actually the system is behaving. So if you look carefully, then you see that this is the profile of consumers, where the vertical line indicates the current time. So we just passed 10 o'clock. That's Central European time, by the way. And on the left, you see the actual values, and on the right, you see the predicted values. So there's a prediction for the consumption based on historical data. Then the orange is the production, the actual and the predicted, based on the forecast services we have both for solar and for wind. And the third one is the storage device, where you actually see, in this case, the set point powers, which are controlling the battery and set by the system, where you clearly see that it has been charging in the night, is currently discharging or just stopped discharging probably, and will charge again around noon to be able to discharge again at the early evening, 5 o'clock. Below it, you see some KPIs just set and configured for this application. So numbers like, and I hope the self-explanatory, the self-consumption of the system, currently 34%, the autarky of the energy autarky of the system. So how much of consumption is actually coming from direct local renewable production. That's the definition of the energy autarky. The optimization, the financial saving, which I showed earlier. The storage energy level percentage. So here you can clearly see, as it's a week view here, we selected the week view here, is you see a typical profile of trying to discharge 2 times per 24 hours. And you see the current tariff, so import tariff and export tariff. These are costs. So the export tariff means, of course, that there's an earning of 1 penny per kilowatt hour. That's really brief. I realize that there's all kind of settings here and configuration tools for installers and integrators. I haven't gone through due to time, but I might be able to do it later if you have specific questions around that. What I do want to show is the other locations. So this is Arnhem. So Arnhem is a different situation. We're looking here at a kind of virtual optimization over virtual in terms of it's really connected. But it's not behind a physical single meter. It's distributed around the city. So distributed is a better name. Here we're connecting all the public chargers, as you can tell, around 250 charging locations, 500 charging points across the city. There's also a battery here on the Kleefse Waard, a large solar field. And in this case, there is also shore power, which I just mentioned at the introduction, and there's 3 large wind turbines, 3 megawatt wind turbines allocated in Arnhem. So similar, just quickly showing that this is just a similar structure. The only difference here is that consumers are cold ironing. There's charges allocated. Production is not only solar but also wind, and there's a storage system here. The one thing I wanted to show here quickly is the when-then flow example. So I've just created one quickly just to show you. So what the when-then flow allows you as an application manager is to create simple rules with a left-hand statement, in this case, which says, well, if the storage device, the energy level is greater than 400 kilowatts hours, that's 90% of the, or 80% of the full capacity, then you have an option to right-hand side to perform an action. And the action can be controlling something, or one of the assets within your system, or in this case, it's set to send a push notification to the users. Of course, emails are possible as well. And in this case, I've selected to send it to a user, and this user is Peter. Peter is one of the, or in this case, the application manager within the Arnhem pilot. And of course, you can set a message here. So the message is, there's a default setting here, but you can change the title and text of these messages. And you can schedule these. Now, I won't go through all the details, but you can, if you want, schedule this rule to, for example, only be performed during weekdays and not over the weekends. That's the one I wanted to show for Arnhem. Quickly going to Schwäbisch Gmünd. Schwäbisch Gmünd, I only wanted to show the asset tree on which you're currently seeing on the left. The difference here in Schwäbisch Gmünd is that we're connecting charging hubs of light electric vehicles, so scooters, electric bikes, and what you're seeing here is a couple of different locations within Schwäbisch Gmünd, managed by Unicorn, hence the name Unicorn Engineering. The one I just opened is this is fully operational. So what you're seeing here is the hub at Tannheim. Tannheim is not in Schwäbisch Gmünd, but in Austria. That's because one of the engineers is based in Austria, and they have a hub there. Sorry for the confusion there, but there's one charger and one vehicle currently connected. And as you can see in the B2B location, which is a factory in Schwäbisch Gmünd, you see one vehicle connected and two vehicles connected. So there are 3 chargers here, and 2 out of 3 are currently being used by a vehicle which is being charged. So this is an example of a fully operational system. Each of these locations, or some of these locations, have batteries and solar. So like the office location has a storage device as well as a solar system. So it's kind of a standalone system. The others only have chargers in place, and they will take into account the limited capacity of the connection. Last pilot implementing in, oh, sorry about that, is the Stuttgart case, and the Stuttgart almost looks the same as that's currently being implemented. Stuttgart, there will be multiple locations. There are currently 2 here, as you can tell, Stadtdekanat and Domkirche. And these will be hubs which have a static battery, a couple of chargers, and again, light electric vehicles being connected, and then on multiple hubs as well. So this is kind of similar as in the Schwäbisch Gmünd case. I realize I'm a bit quick here, but I want to keep the presentation limited and leave room for questions. I did want to go back to the presentation. So I hope I've briefly explained the elements of an energy management system, especially by showing the examples. An important next question would be, yeah, but why would I want to apply an energy management system? And a couple of reasons. Most importantly, the reason of striving for a minimum carbon exhaust by maximizing self-consumption of renewable energy, and reducing or limiting the electricity cost by controlling the consumption of electricity and controlling EV charging sessions. Next to that, there's obviously the technical or functional benefits of just having the ability to have a live overview of all your energy flows. Also important to be able to actively monitor your system for maintenance purposes. So the rules would allow you to get triggers when any of these systems, which obviously in the end would get quite complicated, is non-performing, and send off notifications to any of your service providers. And last but not least, there's some more social benefits, just to create the awareness of sustainability. Is simplified as you can define KPIs which you can follow and communicate with users or stakeholders within your city. So what would I need to realize such an EMS? Of course, you need a system, but and that's a warning here. Realize that, and it will be this slide and the next slide. There needs to be things in place before you can meaningfully apply an energy management system. And first and foremost, it's about people. And if you want, as a city or a larger entity with your own campus, want to apply such an EMS, you need a couple of rules. And first of all, the energy managers. To actively manage the system, you would need to have a fleet manager in place who can orchestrate the usage of a fleet and can set energy schedules. Of course, there's the financial management side and auditing the business case. Is there a business case for an energy management system, but also audit the actual savings being achieved. And last but not least, the technical part. This is something we often see missing, is if you want to successfully implement an energy management system, it's really crucial that in any tenders you're doing for the different systems, whether it's vehicles, whether it's chargers, whether it's solar, you have the correct technical requirements in the requirements specifications. And the last tier, IT department, of course, you need to actively manage an EMS application for a technical functional point of view once in place. The other category of requirements is more, I call it strategy related. There are two kind of ways how you would strive for optimization. One would be as a city, within your own ownership and control. And in that case, it's relevant that you have both legal as well as financial ownership of all the parts. And it's a bit more specific. If you don't have the ownership and full control of all the elements in the system, then you might end up negotiating between different providers and different owners of different systems, which might have conflicting commercial models or business cases behind it. So if you don't treat that as one entity and can't organize it like that, an energy management system would be bound to fail, or at least would be very hard if you can't compensate everybody as part of the system. Another approach here would be make use of the emergence of energy communities. There's a lot of activity by citizens to create their own energy communities. And the other approach could be, because we're talking a completely open source solution, is that you enable them to manage their own optimization groups or energy hubs by collectively producing and using energy and controlling that to maximize the local energy, renewable energy usage. The third requirement here, and I already mentioned it with the tendering, is the technologies side. Be aware that in any tender you secure that you have live access to data, not only to read it, but more importantly also to be able to control the devices you'd want to control. So we're talking chargers, maybe thermostats of HVACs in buildings, batteries, electric fleet. So in any procurement, you need to be able to safeguard that you can actively steer those. What are the steps to take to implement it? Be aware, another warning here is that before actually implementing the two steps which you need in front, before first of all design a balanced system. So if there's not a properly balanced system between production and consumption, then the unbalance will mean that you've spent either too much money and or optimization doesn't have a benefit because there's not enough renewable energy, or there's always enough. And you secure in the procurement that the requirements for these systems are in place. So to be able to have actually an EMS on top of it. And then when you go for an energy management system, of course, the integral project management is crucial. We've seen that in the different locations. And once in place, don't forget the use and service and the active steering of such a system. That's not only by the energy manager, but it's also from a more technical functional point of view by application support or ICT support. The last slide I have here is, so open source. What does open source energy management system mean? It means that the code base of the complete energy management system, and I want to emphasize the complete side of it. It's all there. It's published online, and you can freely use it also for commercial use. So the license of this is all free. So if I look at the self-service side, you only would require hosting, and hosting you have to run such a system somewhere. And if you go to the typical service provider here, whether that's OVH in Europe, or whether it's more a global provider like Amazon, you typically require about €100 per month. That's the order magnitude for the kind of applications you just see. And that means you would have two environments running, one to test, one to run in operation. This might already be too technical, but it's a really limited amount. That's not, in most cases, not the cost. And regarding the whole configuration, so during setup, in the self-service, there's an option to do it yourself. And there's documentation. We'll share this presentation later. That's documented. So there's online documentation to explain you and more technical people how you would set up a system, how you would configure it, how you would host it, and also how to configure the energy management system yourself. And that's all done on the wiki documentation on GitHub, which you, as mentioned, can reach through the link. And for the self-service, there is also the service, and it's based on OpenRemote's open source system, and it's part of it. There's an active forum where you can post questions and chat with other users of the system and get their support to get the system running whenever you get stuck. Of course, there's a professional paid alternative. And of course, it's OpenRemote, we offered it, but I just want to emphasize that as it's open source, it's not a lock-in to OpenRemote as such, because the code is freely available. Any professional IT service provider can do this. And the amounts mentioned here are indications of what we believe are the cost of a reasonable proper configuration of a system in your city, and the typical cost per year to service, maintain it, and offer support, whether training or application support. That's in short the presentation I had in mind. These are just some contacts. I'm sure you can find our contact deals online, or otherwise approach the CleanMobilEnergy team. So there should be enough ways to contact us. Would want to leave it with this and hand over to Madeline, or ask you all whether there's any questions.
Thanks, Pierre. Very comprehensive. In terms of just trying to put some context around the nucleus of the interoperable energy management system, what you just described there in terms of Nottingham, Schwäbisch Gmünd and Arnhem was everything from the last mile technology right through to cold ironing and electrification of boats. And to put some scale on that, in terms of Arnhem, I know that there's approximately 23 to 25 megawatts of energy that's supplying the city at that scale that Pierre had indicated. 250 chargers in the city of Arnhem. It's very, very impressive indeed. And also what's really impressive is Nottingham. I would suggest that Nottingham are leading, especially in the UK, regarding the rollout of electric vehicles and vehicle-to-grid technologies. So there's a multitude of mobility parts there, as well as the generation of renewable energy, and how the system then drives down the cost to try and meet the kind of equivalence to what fossil fuel is. But that's very difficult at the moment, because that's increasing in price, as everyone knows. One thing I would say in terms of real benefits is that all cities and all regions now have commonly referred to as net zero targets. You will not meet net zero targets with strategies that are based on paper. What you will need is 4.0 technologies, just demonstrated there by Pierre, and you will need to have that holistic approach. So the demonstration that hopefully that you've seen will start that transition. In actual fact, what you would need to have is some baseline figures so that you're able to monitor that. And I think that was really important that Pierre had described that in the presentation, that monitoring and testing the system is extremely important in the outset as you start that transition towards net zero. If you're looking at a 10, 15, 20-year strategy, then the implementation of dual flow energy management systems is extremely important. I maybe just start off with a couple of questions. We've got 10, 15 minutes. My question, Pierre, really would be, if I'm a city and I've just described, that I have now a policy and that is net zero, and that we need to drive down our dependency on fossil fuel. How does the iEMS support me in that transition, and is it future focused? If there is, let's say, other renewable energy sources that come to my city or to my region, can the iEMS support that, let's say, in 5 years? Can I change the dynamics of the system?
Thanks for the question, Chris. Actually, I hear two questions. So first of all, let me emphasize, and I also did in the presentation, before you start implementing an EMS, you need to design a proper balance system so that there's a balance between the renewable generation versus the consumption. That's one. Your other question is about let's say, the future proofness and the flexibility to grow or change over time, as nobody can predict the future, and you need the flexibility. And maybe best to let me go back to quickly sharing one of the examples. Let me go. I should take the full screen here. What I want to do is go back to the example of Nottingham. Can you see Nottingham now?
I think it's loading. I think it's loading.
Well, we can see the screen.
Yeah.
But you have to select some.
Yeah. So you see the list of Nottingham,
yeah.
right? Yeah. So the reason why I was here is that what I have showed you let's say the daily usage, but what I haven't showed you, if you an installer and you're installing the system, there's many options here, and I'm not going to bother you with all of these, but there's things like users and roles and the whole management of the system. Again, I'm not going to touch it here, but what I would want to show here is in your example, well, if you would want to add to your optimization, and I'll do it on the spot here, you can, if you have the correct rights, of course, you can add another system, and you can add another system. And there's two pieces of doing that. First of all, and we call them agents, and basic agents are protocols. So these are technical ways of connecting to external systems, and you see a whole range of them, some of them being generic, like for the technical people in the TCP or HTTP or MQTT. And these allow you to make a connection to a new system. And so imagine there's a new renewable energy source which we don't know yet about. You could first of all make a connection to this system, and the second one you could do here is, and let me just show that there's a series of asset types, and currently these are defined as they are, but you can create another asset type. And then, for example, if that asset type is in, say, well, I want to add it. So I'm just as an example, that new asset type, we haven't defined it, so you can't see it. But for example, I can add a wind turbine here, which is new, and I'm adding it to the optimization group, and you see it now appearing here on the left. And then in a modification mode of modify mode, I can configure this system now. I won't bother you with the details here, but I just want to give you some pointers that the system would allow you to configure the connections to new systems, even set up new optimization groups. So there's an optimization one here as well. So here it is. And I want to have a new location. And you can imagine that the moment I add this, and I'm saving this. So you see now a new location appearing here, and again I can make a new structure here and have a complete new location with new what we call assets or producers under it. So this whole configuration makes it suitable for technical people to install the systems, as well as adjust it towards the future.
Okay, great. Thanks for that. It appears to be fairly straightforward. It has all obviously the GPS locations, etc. And it's almost a menu and a drop box that you would use. We've got a couple of questions, Pierre. One from Christopher Hoff is saying, can you give some information on the data models that are used? Are they European standards? Are they global standards?
Yeah, so the system is built up. We see that there's, from the agent, so the connectivity perspective, of course, we can connect to standardized protocols if they are available. And we see the reality, unfortunately, is not that they're not. So in many cases, protocols are generic ones, HTTP based, for example, MQTT based connectivity. But that doesn't include a model. And the way OpenRemote is set up, and that's what I quickly showed you with the assets and the asset types. You can set up your own models within OpenRemote. So if in your location you say, well, for me, a charger is a device which has a power, a set point power, an energy in, meter in, energy meter out, which are obviously obvious attributes, of course, that any meter or any charger would probably have this, or a lock. For example, your charger has a lock, some others don't. So OpenRemote offers the flexibility to define your own models using asset types.
Okay, that makes a lot of sense and makes it a bit more kind of practical and kind of answers the question that I had posed initially regarding the future focusing of the system. We've got two more questions. One that came in and for some reason it disappeared because the last came from Ian Whittaker. I'll come back to Ian. One question here from Saoirse is any particular critical lessons learned worth mentioning at this point, especially concerning the realization of communication between different assets of the iEMS? Has there been a variation in terms of, Arnhem is quite a large city, so is Nottingham. Schwäbisch Gmünd is only population of 60,000. So there's a range of the operational aspects to the iEMS. Well, what lessons have been learned from the development point of view, Pierre?
Yeah, I think I mentioned a couple during the presentation, but I think if I would have to pick one which I would consider being the most important, then if you're a city, the most important is the preparation up front. So I can't stop repeating saying, well, be aware that in your tendering of your different systems, take along the technical expertise of these systems and an energy management system to put the correct requirements in terms of connectivity to systems. What we often see happening is that, yes, we need cloud APIs, for example, and then it's left by that, and maybe referring to some kind of standard, but then still in the auditing these, the ones inputting or submitting, there needs to be you need to be on top of the exact requirements in terms of offered technical connectivity and actually being able to deliver. We've seen many examples where it was verbally confirmed that it was there, but when digging in and trying to realize there was a lot of work to be done to make it accessible. That's a bigger problem than standardization, I would say, because especially larger companies, when they do an implementation, they're mature enough to do a proper quality HTTP REST based kind of API well documented. So once it's there, it's not a rocket science, or it's not too complicated to implement. It's a lesser of a problem. So that would be the most important thing to take into account. So the preparation side.
Okay, thanks for that. I have one question, and I'll have the last question for Ian. My question, I think you've already indicated, where you showed Schwäbisch Gmünd, and you showed one of the employees of Unicorn Engineering who resides in Austria. Let's say we have a rural area. Let's say there's a local authority that's in a very rural area. They have distributed assets. Can it function the same way as a city in terms of the iEMS with distributed assets?
Technically it can, so you can structure the optimization groups in whatever way you want. Whether you achieve your financial carbon goals would depend on the contracts you would have. So if you as a city are able to sign an overarching contract for a region as being 1 meter, so only looking at live total production, total consumption, that of course would be the key condition requirements to make this successful. If you can sign these kind of contracts, even with agile tariffs for regions, I would definitely recommend looking into that. If you use an EMS, agile tariffs will benefit. You will, in an operational system, benefit from it. Being able to sign these contracts is the key. Once you have that, then from an OpenRemote point of view or EMS point of view, it doesn't matter how distributed your systems are, as long as you can connect to them.
Okay, thank you. And final question, it came in the chat, and apologies, Ian Whittaker, could you maybe just ask the question if that's possible? No, I did see the question coming. Oh, I think he's. Yes, thanks, Ian.
Yeah, I think it's my internet a tad slow. Yeah, I've just understood that there was different ways that you could sell the electricity back to the grid. You know, half a dozen different ways. So if you've got something that is fast acting, I believe you get more money for providing quite big lumps of power very quickly for the frequency response of the DNO. I just wondered if that system was capable of sort of doing that at a later date, if the capacity is there to dump it back onto the grid fast.
It would depend on how you would install it. So the typical structure, which we currently have, is that the overall EMS is cloud hosted and then linked to different subsystems, which you can imagine from different suppliers. But technically, it would be capable of doing what you're looking for, frequency response. So just monitoring the delta in frequencies and then responding within the legally required setting to change, for example, discharge a battery, for example, if you have one. That would merely require the installation setup, so that you properly set up on a local server within that local system, directly connected, wired through your battery, for example, added to your battery management system or allocated next to your battery management system. It's merely the configuration and where you set it up to safeguard that it will properly respond. But technically, yes. OpenRemote will be capable of doing that, or the EMS will be capable of doing that.
And just to add there, Pierre, obviously that's exactly what we've been looking at in terms of the V2G equipment and the battery equipment, and both those can do that. And the iEMS control in the terms of Nottingham will be an overarching look at that. Depending, there's a lot of developments happening on tenders, but that was the original idea, that the battery V2G outputs and DSR will be managed from those suppliers, and then we'd be able to monitor it and ahead of, you know, the great thing is that in the future we could put all controls up to the very top.
And then And I think in the Nottingham case, if you want to do this with EMS, you would probably safeguard that the EMS would be running on site, wired to the local system to prevent too much delays, if any, or in internet connectivity dependence.
Great.
Yeah, well, even our HV sub, there's connectivity for switching like wireless, and we've had to test those things. So yeah, these are all things we'll look at once we've got the final equipment sorted, and then we can look at that full integration.
Thanks for that, Steve. So but I know we're running just about 5 minutes. I really want to wrap up now. So thanks, Pierre, for the overview. Thanks everyone for attending the second session of the digital series of the CleanMobilEnergy project. We have a few other events planned in the next number of weeks and months. But hopefully the digital series will end up as a face-to-face series, as I think everybody wants and desires to have. I thank you for attending. If there's any further questions, you can come back to myself or Madeline or Pierre. The presentation will be uploaded onto the CleanMobilEnergy website. There's lots of activity within the digital media profile of the project. Hopefully that gives you a good overview of the benefits of an iEMS system. As I say, most cities and most regions will have to implement such. There's no other way that you'll get to your net zero targets. It needs to be enabled by technology. I'm not suggesting for one moment that technology will get you there. As Pierre had mentioned, people and technology together, that collaborative approach will get you to your net zero targets. So it was very good questions that came forward. As I said, if there's any others that you wish to ask, please just come by email or through the social media channels. So I wish you the rest of the day a good day, and keep safe everyone, and keep in touch, and we will certainly be in touch in the very near future. Thank you.
You're welcome. Thank you.
Thank you.
Bye-bye.
the recording and then it should save. So hang up with me, go back into the chat on your Teams and then end the recording and then.
Yeah, done it.